Good afternoon. So I want to talk about rethinking unsupervised learning. To get started on that, let's make sure we all know what I want you to understand by unsupervised learning, and I mean classical unsupervised learning. So there's this classic picture that differentiates machine learning from programming. Programming, you have the data and the rules, and you do your programming, and then that gets you out the results you want. Machine learning works the other way around. You have the data and the results you want to get, and you hand that to the machine learning algorithm, and it spits out for you the rules that you're going to use to do that. But that's a slight lie, because that's just supervised learning. In unsupervised learning, you get the data and nothing else, and you have to turn that into something, some results, somehow. So what do I mean? Well, given you've only got the data, you're going to have to get out structure. But what do I mean by structure? Well, it has to be something inherent in the data, probably about the geometry or structure of the data itself. And what that means in practice is things like clusters, or density estimates, or a low-dimensional representation of the data, or outliers and anomalies in the data, or even topological invariance in the data. And the algorithms for this date back over a century. Clusters and clustering algorithms, the standards there are k-means, which is 1956, and single linkage, which was from 1957. So we're already like 70-year-old algorithms. These are still workhorses that do the job today. Everyone is still using them, or slight modifications or updates of these. If we're talking density estimates, well, there's not much to that. You're either doing histograms from 1892 or kernel density estimates, which are nice and modern from 1956. If you want to do low-dimensional representation, you can use principal components analysis or some slightly more modern variation of that, but that dates back to 1910. Or maybe you're doing slightly more modern manifold learning and you're using ISOMAP or TSNE from 2000 or 2007 or something slightly newer. But we're talking about algorithms from, at best, the early 2000s. If you want to do anomaly detection, you're using standard scores or z-scores. People still use this all the time. This is still a workhorse. It's doing the job. It's from the 1910s. You might be using something fancier like local outlier factor from 2000 or isolation forests from 2008. If you want to do topological invariance, this is one that doesn't date back forever. It dates back to 2002 was the first time practical algorithms for doing this on data. But that's persistent homology. It's recent, but it's not that recent. So now I want to pivot completely and talk about unstructured data. So a catch is that many algorithms, these classical unsupervised learning algorithms I'm talking about, were designed for tabular, low-dimensional data. The classical data that you found in 1910 or 1956 or 2000 or 2010, let's be honest. But we now live in a world where neural embeddings have just unlocked a vast store of unstructured data. Text, images, video, audio, you name it, there's an embedding model that will embed it into a vector space and allow you to do interesting things with it. You can have giant collections of unstructured data that previously you just couldn't do anything with. And now you can do all kinds of interesting things with them, convert them into vectors, and they're your oyster for machine learning. But they usually have hundreds or even thousands of dimensions. So what can we do with it? Well, let's just apply that list of things. We could cluster the embeddings. We could do density estimates for the embeddings. We could do visualization with dimension reduction. We could do anomalies in the embeddings, topological invariance of the embeddings. But what does that actually mean in practice for you? Well, an example of clustering the embeddings is getting topics and documents. Density estimates, maybe you're trying to understand the distribution of images in a giant image data set. Visualization could let you explore an entire space of audio samples. If you're doing anomaly detection, maybe you have a giant pile of documents, and the anomalies are going to be the ones that were in the wrong language or a different language than the one you expect. So there's lots to find in here. Topological invariance actually turns out are really great for finding adversarial examples for machine learning techniques. So there's a lot of value in doing this, but there's a lot of challenges for this high dimensional data. And my ambition here is to try and convince you by the end of this talk that you don't understand high dimensional space. So the algorithms I talked about are all rooted in intuitions from geometry that you can think about, nice 2 or 3 dimensional examples, and they don't magically just work in high dimensions because high dimensions are strange. It's really non-intuitive. So let me go through some examples and try and convince you that you don't understand high dimensional space. So in 2 dimensions, I can inscribe a sphere, a circle, inside a square, and I can look at the ratio of that sphere to the ratio of the area of the square. It doesn't take up all the square, but it's most of it. In 3 dimensions, I can put a sphere inside a cube. This makes sense. It's most of the box volume. It's not all of it. It's slightly less than the circle takes up of the square. As dimensions go up, the ratio of the volume of the sphere to the volume of the box goes to 0. All the space is in that corners of the box. None of it is in the sphere. If you start with a sphere and add an epsilon thick, however thin you want to make it, epsilon thick shell around it, what's the ratio of that original ball compared to that epsilon thin shell around it? Well, in 2 dimensions, it's just a little thin shell. In 3 dimensions, you maybe get a little more volume in that shell. As the dimensions increase, the ratio goes to 0. All the volume is in that epsilon thin shell. And in fact, no matter how small an epsilon you pick, you can choose a dimension high enough such that all the volume essentially lies in that shell. Far more volume lies in the shell than in the ball itself. Here's an interesting one. Let's take a box. We're going to put spheres in the corners of the box, and then we're going to put the biggest sphere we can that packs inside in amongst all those other spheres. What's the ratio of the box diameter to the sphere diameter? Well, in 2 dimensions, like the sphere diameter is tiny. In 3 dimensions, it's a little bigger, but I mean, obviously this is going to be limited by how big the box is, right? No, it's not. In fact, as dimensions go up, the sphere gets bigger than the box. That doesn't make sense if you think about it, except if you do the math and sit down and work through it. Yes, it does. That's how it works out. The sphere starts poking out of the box, and the ratio goes to 0. Just to prove it's not all about boxes, let's do triangles. We can take a triangle and do an in radius and a circumradius. In 3 dimensions, we're going to get a tetrahedron, and we can inscribe a ball inside it and a ball outside it. What's that ratio? Well, this one goes to infinity. All the space lies in the points in the triangle or tetrahedron or higher dimensional simplex as you go up in dimensions. This is not what you'd imagine. It's not just that the box has these dimension-specific things. Even in tetrahedra, the points of it are where all the volume lives in high-dimensional space. If you want to look at angles of a random pair of points, so in 2 dimensions, we can just randomly select points on a circle and measure the angle between them. In 3 dimensions, we can pick points on the sphere and measure the angle between them. You get a distribution. You can see those down at the bottom there. But what happens in high dimensions as we go up? Well, in fact, absolutely everything concentrates until all the angles pretty much are a very tight distribution at 90 degrees. So in high dimensions, everything's orthogonal to everything else. What about surface areas? Do they behave even remotely sensibly? Well, here's a game. Take a ball in whatever dimensions you like. We'll start with 2. We get a circle. I'm going to draw an equatorial band, so a region of some height about the equator, such that the region of the sphere that lies inside that band, the surface area, covers 99% of the total surface area. So in 2 dimensions, we get something like that. In 3 dimensions, you're talking about a band around a sphere. How high do I have to draw that band to be able to capture 99% of the surface area? Well, in high dimensions, the answer is essentially 0. As you get to higher and higher dimensions, the band has to be epsilon big to cover 99% of the area. And if that vaguely breaks your brain, to make it worse, I didn't impose any restrictions about how I drew that equatorial band. So any rotation of this is also valid and also true, so I can draw that band at any angle I like around that sphere, and that will still all be true. Hopefully I've convinced you that maybe your intuitions and thinking about what high-dimensional space would look like is maybe not how things are going to work, but at least distances are going to make sense, right? If we draw a distribution of the distance between two random points selected uniformly from a ball of radius 1, what happens? Well, as the dimensions go up, this concentrates to a tighter and tighter and tighter distribution at the square root of 2. Was that obvious? Maybe, probably not. This is not the kind of behavior one would actually expect, and it makes distances very difficult to deal with when we're randomly sampling points from a ball, because all the distances look like approximately root 2. It's very hard to tell distances apart and differentiate between how close things are if everything is all root 2 apart. Okay, what if I did a cube instead of a ball? I mean, that should be similar, right? Well, no, remember, in the cube, everything lives in the corners. So in fact, if we sample points randomly from a cube and look at their distribution of distances, the distance just steadily increases as dimension goes up. The distribution stays just as tight as ever, but the distances just get bigger and bigger and bigger and bigger. What about cosine distance? That can save us, right? Well, if we look at cosine distance of nearest neighbors among points randomly uniformly selected from a unit sphere, what we get is that as the dimension of that sphere goes up, everything gets a tighter and tighter distribution at higher and higher values. And so we're just not getting what we actually want out of this. We can't differentiate distances very well anymore. I will show you a trick, though, that will maybe help you at some point. If you, instead of using cosine distance, use the negative log of the cosine similarity, the distances as the dimension goes up slide up and up and up. And the upside of this is that that actually has the same distributional behavior as the Euclidean distances we were looking at before. So if you want distances to behave like Euclidean distance in terms of distribution, this is a good trick that will actually get you there. But at the same time, it still means as we go up in dimensions, things are not behaving the way we would want them to. So given all these weird non-intuitive things and the fact that distances are so badly behaved, what breaks with the algorithms we've discussed? Well, clustering. K-means is based on spherical balls, and I think we've already seen how badly behaved balls are in high dimensions. Single linkage is incredibly sensitive to noise and distances. If there's a little bit of variation in distance, it can completely mess up single linkage clustering, and we just saw in high dimensions, all those distances concentrate. So it's very easy to end up with noise in it. So those aren't going to work very well at all. How about density estimation? Well, histograms are incomputable in high dimensions. That's just immediately removed. And KDEs rely on Gaussian balls and reasonable bandwidth choices. So you need to know that your balls behave appropriately in high dimensions and that your distances are well behaved. We have neither of those. How about low dimensional representations? PCA assumes linearity, which we have a lot less of in high dimensions, and neighbor distances, which all those manifold learning-based techniques are based on, are very sensitive to distance changes. And so, again, that's not going to work very well. If we want to do anomaly detection, well, local outlier factor requires density to make estimates, and you require exponentially more data to get the same amount of density in high dimensions, so local outlier factor won't work. Isolation forests have far too many potential splits to do a good job in high dimensions. They're not going to work either. How about topological invariance? Well, as distance distributions compress, the difference between the noise and the signal just becomes indistinguishable. And so all the persistent homology games you might play also don't work. So in short, everything breaks when we want to do classical unsupervised learning in high dimensions. So what can we do? What sort of kind of works and maybe we can't justify? Because we still have to get our jobs done. So for clustering, one approach is to use UMAP followed by HDBSCAN. Now, I'm obviously biased in this recommendation, but you could substitute in TSNE and another density-based clustering algorithm of your choice. I think that would work just fine. The key is that we need some combination of these two things, something to get the dimensionality down in a way that understands at least some of the manifold structure, and a density-based clustering algorithm that can handle the strangely shaped clusters that we're going to get out of it. But this does actually work surprisingly well on neural embeddings, and you'll find this inside of the Burr topic modeling library, for example. Another approach is a very, very new in development library called Evoke for embedding vector-oriented clustering. I would recommend this one. I built it specifically with embedding vectors in mind. It's not a principled technique. It's just how to do this as efficiently as possible with the techniques we do have. It's very, very fast, and it'll get you decent clusters out very quickly. Okay, how about density estimation? I actually don't know of anything. So if anyone here knows how to do density estimation well in high dimensions, where the results are actually meaningful as opposed to just running KDEs, which return something, please let me know. I'd love to know your thoughts on this. Low dimensional representations, I would recommend TSNE, particularly the open TSNE implementation, UMAP or PACMAP. These algorithms aren't perfect, but they're very good compared to most other things you could try and do. If you want to do anomaly detection, there's actually a UMAP-specific set of parameters you can throw in that tunes it for anomaly detection. And once you've got dimension down, you can use local outlier factor or isolation forests or something like that. Topological invariance, well, you can use reweighted KNN graphs. There's some tuning to do with that. It's not out of the box. And persistent homology on that structure, and that'll get you something that will work reasonably. So what are the lessons learned in these methods that, as I said, aren't necessarily the principled approach, but will get the job done well enough to at least get some results? It's that we need distances on substructures, not in the ambient space. And the right distance can depend a lot on local regions and local structures. And so we need to be able to understand what distance looks like in local regions of the space. So what might a future approach to doing all of this look like? Well, I'm going to start by just rethinking how we're going to do KNN graphs. So our goal is, if the data lies on some substructure, do you know that it's all the same intrinsic dimension everywhere? The answer is no. There's absolutely no guarantees of that. Is it the same sampling distribution everywhere? Probably not. Is it sampled at the same rate all across whatever substructure you have? Probably not. That's a whole bunch of things to try and keep track of, but let's have a look at what happens to each of those things as we go into high dimensions. So the distribution of distances to nearest neighbors, sampling as we change the intrinsic dimension. We saw this before. The distance just steadily increases. The distribution slides up. But each dimension has its own unique characteristic structure of what that distribution looks like. If we are looking at instead the variance of our sampling, in low dimensions on the left, it looks fine as we change the distance scale of our sampling. Everything stays anchored at 0, and the distribution just gets wider. But in the high dimensional case, the distribution slides up the distance scale again, We're not anchored at 0, and we get different looking distributions that are steadily getting larger and larger in distances. If we're looking at sampling rates, this looks very similar to the variance. In low dimensions, this is all very straightforward. The variance just steadily increases, but everything stays anchored at 0. But for high dimensional data, again, we get this slide and change in the mean of the distribution as we vary the sampling rate of the data. Now, an upside of this is that maybe we can latch on to that. So here's some distributions from real data sets. They're still toy data sets, don't get me wrong, but the PyNNDescent data set and the 20 newsgroups data set embedded with just standard sentence transformers embedding vectors. And I'm looking at the distribution of nearest neighbors of different classes from this data. And the thing you'll notice is that the different classes, different groups in the data have very different looking distance distributions. And you can pick out some of them that are maybe made up of a couple of different distance distributions that have been lumped together. Maybe there's a couple different classes of distance distributions. So if we could locally model distances to the nearest neighbor, we could capture intrinsic dimensionality, distribution scale, and sampling rate all at once. We don't have to care about what those actually are. We just have to understand what distance distributions look like locally within a given region of the space. So that's what we're going to try and do. We're going to locally model the distribution of nearest neighbor distances. And fortunately, that distribution is just a one-dimensional distribution, so it's easy to keep track of and to model. We can model it with straightforward standard textbook distributions. And then, because we've got some structure, we can look around the local neighborhood and use what the different distributions that the neighbors of a given point C to refine our estimates of the probability of being neighbors. So here is a data set. This is MNIST digits embedded with UMAP down to 2D so we can at least look at it. And the different digit classes are different colors. And this UMAP does a good job at separating these out into distinct clusters. But I've drawn on the edges from the KNN graph of 15 nearest neighbors. It's a weighted KNN graph, so it decays. But what you can see is that there are lots of edges that span across between these digit classes in a not so great way. These are the nearest neighbors in high dimensional space, but maybe they shouldn't be. This is after 0 iterations of doing that modeling and smoothing that I talked about. After 1 iteration of sticking those models in, doing the smoothing, and evaluating edge weights based on the model's local understanding of what distance should look like, we get something like this. After 2 iterations, it's looking better. 4, 8, 16, 32. Now we're really improving. The edges have essentially all disappeared between the digit classes. I don't know if you can see on the big screen, there are faint ones in there, here and there, but it's not so bad. And by the time we get to 64, we're not getting any further improvement. But what that means is that what we had here is no longer k nearest neighbor graph. Each point can have a different number of neighbors. Some might have more than k, some might have less than k. It's a bunch of neighbors based on the expected distribution of distances to nearest neighbors. And we're going to be able to use that in all sorts of interesting ways. So there's still plenty of scope to improve all of what I just described there. I'm still working on this. I haven't worked out all the details, but I think there's a lot of potential gain here. And it provides a foundation on which we could start to build algorithms for high dimensional data, as an example. So what do I mean by new algorithms based on that? Well, if I want to do clustering, then given that connectivity graph that I just showed you, we can run the rest of a DBSCAN or HDBSCAN-like algorithm on that and produce clusters. Those clusters are good, but many points are going to be declared as noise. But we have that graph structure, which we can still use. We can do Bayesian label propagation across that graph and get out surprisingly good clustering, surprisingly efficiently in a very principled way. If we want to do dimension reduction, That connectivity graph is everything we need to input into a UMAP-like or TSNE-like or PacMap-like layout optimization algorithm, but it's going to be a better graph to start with than those algorithms would traditionally use. If we want to do density estimation, then those smooth local models of neighbor distance provide a great foundation for flexible relative density estimation. If we want to do anomaly detection, well, I said samples have a different number of neighbors. If a sample has 0 nearest neighbors under that model, well, that's definitely an anomaly. And you can broaden that and make soft anomaly detection out of that approach very easily. For topological invariance, we can derive filtered simplicial complexes based on neighbor probabilities and run persistent homology on that complex. So we can do, in fact, all the algorithms we want to do based off this kind of thinking. So just to sum up, the main points I actually want you to take away are be very wary of applying classical techniques to embedding vectors. They will run and they will give you something that you will think is an answer, but it's probably not as good as you think it will be. What we do need is new unsupervised learning for embedding vectors. And that's a lot harder than you might think, because none of the classical algorithms are really even close to getting the right mix of things that's going to make this work. But there are some paths forward. I presented one. I'm sure there are other researchers also working on this right now who have other ideas and other ways forward. And so watch this space, because I think this is actually going to be a growth area, because it's going to unlock the power of all these embedding vectors to be able to apply these traditional techniques and get way more interesting and powerful and meaningful results out of your unstructured data. Thank you.
We're almost out of time, so we can entertain 1 or 2 questions, please. Anyone? While he's going to the gentleman here, any other? So just 2 questions.
Thank you for the presentation. So for the technique you presented, do you need the classes or is it just for validation?
That was just for validation. This is the great challenge of unsupervised learning. There's no right answer because we don't have a correct answer that we know a priori, like supervised learning. So we can't measure against some known correct answer unless we have some classes that we expect to be able to recover. And that was what I was using that for. It provides some level of validation that this is doing the right thing. And so my claim is that yes, it is. And hopefully that's apparent from what I showed.
Yeah, so is the big idea sort of behind what you're trying to do that you've got sort of the intuition of the low dimensional algorithms, and you're trying to develop algorithms that can deal with much higher dimensional data with the same intuition that we use with the low dimensional ones?
In some sense, yes. But we really have to work out what we need to do to translate things into a realm where we can even have sensible intuitions about them. And so the graph-like structure that I was trying to build and show is one way of building a thing that we can now tractably work with. So hopefully that's helpful. I will say, if you have further questions, throw them in the Hoover chat, has question and answer. I'll monitor that this afternoon and answer there, or come find me.